Hello, welcome back. This is exercise 11E.2. We've already seen 11E.1 where we started to learn how to use integration by parts on repeated occasions, and I did explain that you have to be able to do this twice. I want to now look at definite integrals. We only saw last time how to do this for indefinite integrals, so there's a bit of an extension here. So here's my starter. This is not integration by parts. This is a reminder of how we integrate definite integrals with trig functions. So first of all, it's integrating cos. So if you're doing this, I need to remind you that minus sine cos minus sine minus cos, and we're integrating cos. So when we go up, it will become a sine. Now we've got these limits, and you'll notice whenever you differentiate sines and coses and trig functions generally, it has to be in radians. So this is no sort of accident. It will never be in degrees if we're differentiating and integrating. So it's the 5 cos 2x dx, and when I integrate this, the cos is going to become a sine. I've already said that, and it's a positive sign. It says 5, but because it says 2, I've got to do 5 over 2 sine 2x. Hopefully you remember how to do that, but that's just a reminder. And now I put the naught and the 6th of pi in. The 6th of pi, of course, is 30 degrees. You should remember that pi is 180, so therefore 6th of it is 30. And you can, in your head, be thinking like that. But notice I have got to do sine 2x. So that's like, well, 2 6th of pi, or 60 degrees. The reason why that's useful to know is you might remember that sine 6 is root 3 over 2. Or you might remember it in terms of radians, who knows. But I've put that in and I've got root 3 over 2, then minus 5 over 2 times by, well, if I put naught in, even if I double naught, I still get naught. Sine of naught is naught. So that actually will become naught. So I think my answer is 5 root 3 over 4. Don't know what the answer is. 5 root 3 over 4. So there you go. Now we're doing integration by parts again. It's going to be doing it twice. We're going to use the late rule. What have we got? We've got a trig, that's the sine. We've got an e to the x. You can see the trig is going to become the u. U equals sine x. So then we need du by dx. We need a v, and we need a dv by dx. And of course it's the dv by dx that we've got. That's the e to the x. Luckily, when you integrate e to the x, you get e to the x. That's good. Sine cos minus sine minus cos. That's going to get me then, when I differentiate sine, I get cos. Just go down the list. So that's equal to I. And I've already said when you do this with sines and coses, very often you expect to do this twice. So let's go for this. uv is e to the x sine x again, minus the integral of v to u by dx, which is e to the x cos x dx. Notice this is between these two limits. Now, there's a temptation to, to do it all at the end, which some people do. There's a temptation to only put them in as you do it. So really, technically, I should put the naught and the half pi into this expression and then worry about it. I personally prefer just leaving it to the end, so I'm just going to leave it to the end. So what I'm going to do, I've got that e to the x sine x, and I've got this bit still to do. You'll notice this hasn't been dealt with at all. I need to do my u equals my du by dx. And my u is the trig thing, so that's cos. My v and my dv by dx. And that's going to be my e to the x, which if I integrate will give me e to the x. My du by dx now, coming down, is minus sine x. So if I put this in minus, I'm going to put this in a square bracket again, particularly this one because it says minus. So it's uv, which is e to the x cos x, minus the integral of, and it's this lot, which is e to the x times a minus sine x, which is a plus sine x. to the x. So what's this give me? I equals e to the x sine x minus e to the x cos x. Well, first start, when you got that wrong, minus a plus is minus. And this, you'll notice, e to the x sine x, e to the x sine x, it's the same thing. And there's no 4 like we had in another example a while back. This is just a plain old I that I'm going to sum. It's exactly the same as I started with. So I'll move the I over. I now have 2i equals e to the x sine x minus e to the x cos x. Notice the minus I became a plus when it moved over, and therefore my integral becomes a half e to the x sine x minus a half e to the x cos x. Now this is not the end of it, because all this has got to be in the limits 0 to half pi. So this is the first time we've seen it. Having got to this stage, now we've got to put limits in. So half pi is basically 90 degrees. So if that's 90 degrees, sine of 90 is 1. So you can do this on your calculator, or you can just chuck it in. So it's a half of e to the half pi. That's not very nice, is it? Times by 1 minus a half of e to the half pi. But you've not seen e to the half pi before. Now cos of 90 degrees or half pi is actually 0. So that's times by 0. So that will disappear. I'll put that in a curly bracket. And then I've put my half pi in, and now I need to put my naught in. So I put my naught in, it becomes a half e to the naught. Sine of naught is 0. So minus a half. Now I put the naught in again. Naught. E to the naught again is both of these become 1. And I don't know really why I've left it as e to naught. Really, that's 1. E to naught is 1. And then it says cos of naught, and cos of naught is 1 as well. Ah, right. So eventually I'll get an answer there. So I get a half e to the half pi times 1. That all disappears. That disappears. Minus and minus is a plus. And 1 times 1 is 1, so times by the half is a half. I think that is the answer. Let's see what the I said the answer. Half e to the half pi plus a half. There you go. So that's 2 examples done. We've got a third example here. I'm not sure how many examples there are. Probably not many. This probably is the last one. X squared. This looks like algebra. Exponential. So I'm going to write u equals x squared. And therefore I get u by dx. dv by dx. I do like e to the x because when you integrate it, it's still e to the x. And this becomes, rather than x squared, this becomes 2x. So this is my I that I'm trying to find. So my I becomes, well, it's uv. So it's x squared e to the x minus the integral of these two times by each other, which is 2x e to the x dx. And of course this hasn't been sorted yet, so I need to write u equals u by dx equals. Now the u is going to be the algebraic there again, because the other term, of course, dv by dx, is exponential, and we've already said whenever you get exponential, it's the bottom one. At the top, integrate e to the x is still e to the x. Differentiate 2x is 2. So my I now is x squared e to the x minus, better put this in the square bracket, so it's 2x e to the x minus the integral of those two times by each other, which is 2e to the x dx. And what's this? So this is x squared e to the x minus 2x e to the x, and this one's nice, you don't have any I tricks. If I integrate 2e to the x, I get to the x, so minus 2e to the x. But it's not done yet because I've got my limits, which are 0 and log 2, which is not very nice, log 2, but you often get log 2s and stuff. So x squared, let's put log 2 in that, it's log 2 squared times by e to the log 2. We'll talk about that in a bit. Minus 2 log 2, I'll put the times by e to the log 2. Minus 2e to the log 2. That's right, so that's what I get if I put log 2 in. And then I have to take away what I get if I put 0 in. And 0 is quite handy actually, 0 squared is 0. So 0 squared times that will give me 0. Minus 2x, well that's 2 noughts, so that's minus nothing. This one's different, minus 2 lots of, there's no naught there, so e to the naught. Alright, I think that's done. Now log 2 squared, I don't like log 2 squared. The one thing I do like is e to the log 2. You can see that kind of sorts itself out. So I think this is 2 lots of log 2 squared. I don't think I can do anything with log 2 squared. It doesn't mean log of 2 squared, which is there's that log rule, because it means log 2 times log 2. So minus, this again cancels, that gives me just 2, minus 4 log 2, effectively that 2 times by that 2 gives me 4. And the last thing, they cancel, minus 4. Minus nothing, nothing. Oh, right, minus and minus. And e to the 1 again is really just 1. So 2 times 1 is 2. So minus and minus, I think plus 2. So what do I think? I think it's 2 log 2 squared minus 4 log 2 minus 4 plus 2. I think it's minus 2. Let's see if I get the same answer. I get a plus 2. I just need to be a bit careful at the end. That bit is right, minus 4 log 2. I've got a plus 2 there, and that bit might be worth having a look at. And I've just spotted my mistake. It was a bad mistake, actually. Look at this. I deliberately put this in a big square bracket, so I didn't make this mistake. Minus and minus is a plus. So when I do this here, that should be a plus, and that should be a plus. So that should give me plus 4. This is now minus 2, which gives me overall plus 2. So my answer now is plus 2, and it now works. So, bad mistake, but I found my way eventually. And you know, it can cost you quite a lot of marks that if you're not careful. So in class we will have a look at exercise 11E. We've already started this. We'll do a few more questions of the definite integral types and try and finish off exercise 11E in class as best we can. Okay, thank you.